Xuefeng Liu from Tokyo Women's Christian University. He's an expert in applied mathematics and is going to talk on the computer-assisted solution existence proofs for the Navier-Stokes equations in 3D domains. Please join me in welcoming.
Okay, so the proof is for the Navier-Stokes equation. Navier-Stokes equation is about fluid. So let's go to the. So there are two parts. So the first part is about the current result. So on the solution verification for Navier-Stokes equation, and the second part is something ongoing project. So not finished yet. There are many difficult problems. I would like to share with you something. So, of course, Navier-Stokes equation is very famous, but I would like to introduce some basic thing, maybe because I see they're young students. So, to study the fluid, there are so many, too many ways, and so there are many settings. So here we are considering the incompressible fluid. So the equation basically is something like this. So the U is the velocity field, and you see we can. So there is a different derivative with respect to t, and also the Laplace diffusion term and convection term, and also pressure. Because we are considering the incompressible fluid, the Darwin-free condition appears there. Of course, you see, they have a well-posed problem. We also introduce some boundary condition. This is a very general image about the equation, our objective. So maybe you know this is a very famous medium right problem about Navier-Stokes equation. So something like this. So because the Navier-Stokes equation is something equation which include inside. So about solution behavior, there's many things that's still open. So this is about the existence and smoothness of the Navier-Stokes equation. So prove or give a counterexample of the following statement. So this statement is about, you see something like this. So we have initial condition. So whether the solution is smooth or not. Sometime maybe after finite time, the solution can blow up. So this is a very famous problem not solved for the moment. So okay, here are some results. For 2D case, basically it's clear. So 2D case. So and for 3D, there are some results, but under some special condition or some assumption. So, of course, there are people working on this equation from the theoretical part, use pure mathematical analysis technique. And also we can use computer to do some simulation. So, but you see, because the numerical computation will introduce some error. So something like this. So this is from the statement about this prize from the Clay Mathematics Institute. So many numerical computations appear to activate the blow up solution for the Euler equation. The Euler equation means that the epsilon is 0. This is about the viscosity term. So the blow up means, you see, for example, velocity can increase greatly, it tends to infinity. The numerical result implied that there is the blow up, but you see the numerical computation, so it is unstable. uh, uh. Let me try again. No, now it works well. Nice. That's nice. So yeah, we are using floating point number, and there comes many error. For example, the rounding error. So how can we obtain some result that can be used for mathematical proof? So here we are using some technique from computer. So you see next page. Something wrong? Let me see. Okay, not too much. Anyway, okay, so here. So, wow. Last page. Okay, anyway, for the moment. So you see, we know the IE 754 standard. So this is about floating point number computing. So generally, we are using this standard, but only for one mode computation. Basically, there are four modes. So if you calculate 1/3, so we can request the CPU, the computer, to return result that something like rounding to minus infinity or to the infinity. So for example, if rounding to minus infinity, we can have a lower bound of the true value. And also we can have upper bound. Of course, this is a very rough lower bound, upper bound. In computer, for each operation, so we can obtain true upper bound and lower bound for each value. So, am I lucky? Maybe let me try to share again. Okay, now it works. Okay, so we can introduce the interval arithmetic. So interval arithmetic, you see, for each number, we can have some lower bound, upper bound. For example, pi, we cannot express pi exactly in computer, right? Yeah, but we can have some rigorous, correct lower bound, upper bound. So this is the interval. So pi is inside. We can also perform the square computation. We have something like this. So the interval, yes, will change. And also we can calculate reverse. So you see, in numerical computation, there are many classical algorithms we can utilize for computation. For example, for linear system and unvaried problem. But if we prefer rigorous result, given A and B to obtain a correct solution to this linear system, so we have to use some very new novel algorithm. The existing one, most of them does not work because many more methods only return approximate solution, so not exact. So there are people working on how to obtain rigorous results. So of course we cannot have the true solution. Ax equals b, so we cannot have the true solution, but we can have a solution at interval. So each element is an interval. So interval gives upper bound, lower bound. It means the exact solution exists in this interval. This is what we can do using computer. We are not having the exact value, but we have the exact lower bound, upper bound. So this information is correct. It is mathematically correct. So yeah, for example, for the rigorous unvalued bound or matrix. So basically, if we want to have rigorous result, we should use very special algorithm. For example, we use the Sylvester law or inertia and also Getch-Gordon circle theorem to have the rigorous bound for each eigenvalue. I would like to introduce some example. Okay, it works. So to draw some image about interval. arithmetic. For example, this is a test function, test matrix. Aij, each element defined by something like this. We can apply the rigorous computation algorithm. So basically two steps. One is the rough lower bound for lambda k using the Webster law or inertia. The second step, we use Kato, Lehman, Gaudi's theorem. So they are very specially designed algorithm. So for example, to compute it for the smallest eigenvalue, so let n be 30,000. So a relatively large matrix. This is a dense matrix, right? And also the condition number is relatively large. So if no parallel computing, so in my workstation, so to have rigorous result, it costs about 1 hour. Yeah, this is matrix. Okay, we can compare with some approximate computation. So because this matrix is not so good, so even for approximate solution, it take about 15 minutes. If you want a rigorous result, you should pay more time. Yeah, more effort. Of course, we can use parallel computing to have some faster computation. For example, with 16 processes, we can got the result. We can obtain the result in about 7 minutes. We can use the power of the parallel computing. Another result is about the precision. Okay, let's consider there's some delay. A different screen, yeah. Maybe let connect again. Maybe just disconnect and try. Something wrong with this one. Let's just do it again. Let's close. No, it's okay. So the test matrix something like this. So this is a generalized eigenvalue problem for matrix. So given A and B, how to calculate lambda. So here about the precision. So you see, given matrix AB, we can use Kalexo method to have rigorous first approximate solution. For example, the first one, something like this, lambda 1 has the approximate value like this. It looks good, but if with only result like this, we have no information. So until which digit is correct. So, but we can use rigorous computation to have lower bound and upper bound. This is the rough result. This is sharpened result. This means upper bound is the lower bound. The digits in red mean they are different from each other. So the leading digits are the same. So it means you see the digits until this 9, they are trustable, they are correct. So this is from rigorous result. Of course, you see in this computation there are some rounding error, but because we are using the interval, we can have correct both lower bound and upper bound. And also the precision is not so bad. You see this matrix of a size of 1,000, and the first one and the last one, yes, you see. So interval arithmetic, so it is helpful to help us obtain rigorous result. So now we go back to the main topic of this, okay, about the Navier equation. So first, let's consider the stationary solution. So we are considering the Navier equation defined on a 3D domain. So this is the pure Navier equation, nothing simplified. Yeah. sometimes we can simplify the model to do some analysis here. The equation like this, an incompressible fluid, so it's Dalton free, and we are considering the homogeneous Dirichlet boundary condition. U is 0 on the boundary. So we consider this equation in the form of equation of functional. So this is about mathematics. So I hope this is not a headache for you. So anyway, so let's introduce space V. So V is 1, 0, 2, 3. It means that you see, because it is in 3-dimensional space, in x, y, z, in each direction, we have the velocity. And on the boundary, it is 0. And divergence free condition there. And 0 space, we start. And we define some operator. So this from V to its 0 space, and also this nonlinear operator. Because you see, for A, basically given U, we can regard this U as fixed or some parameter, and then apply it to some function. So this is functional. So this is basic linear operator. And here, because the convection term is there, so it's nonlinear. So we can combine them together to have this F. So Navier-Stokes equation now become very simple. Fu equals 0. Yeah. So the final equation is simple, but basically it's everything inside. So the linear terms and nonlinear terms. Yeah. And also the given F. This is okay, the body force, something like that. So now, so given the equation Fu equals 0, so we are using the very correct method, Newton method. So in lecture about numerical computation, maybe the first lecture is about the Newton method. So here we are using this method for the equation with unknown thing as the function. So because U is the solution, so it is something like this infinite dimensional space, because U exists in this space we write. So the number of bases, okay, the infinite. The basic idea is something like this. First, we have some U hat approximate solution. We can use many. We have so many choices: a new FEM or FVM or polynomial or spectral method. Let's assume we already obtained some approximate solution U hat. So yeah, this is approximate, man. It's not possible. So we consider the first derivative about this F. So F is the functional we defined in last page. So we can consider something like this. This is the inverse of the operator and the norm. So this norm bounded by some quantity alpha. Yeah. You can see if U hat is exact solution, then this is 0, right? If we have good approximate solution, this one almost 0. It means alpha is expected to be small. Okay, alpha can be small if the U hat is good enough. So of course, there are some operator here. This one basically like Jacobi matrix or infinite dimension cases. So here the infinite dimension space, so we cannot not as simple as the Jacobi matrix. Anyway, so some operator there, and also we need some some ball with center with U hat at center and the radius at double alpha. So we have another inequality. This is about the continuity. So the fresh derivative of F, so VW less than something term like this. So it is about continuity. So this omega, we cannot expect this one to be 0. Okay, we have two quantity alpha and omega. Then this theorem about the Newton honorific theorem. So it declares that if alpha omega the production is less than half, then this equation has a unique solution in this ball, and with the radius like this. So this theorem is very important. It's something like this. We can apply Newton method to have some approximate solution. So this is well known and well used in engineering and and also in mathematics. So, but here this theorem can tell us some further information. So this is about the range of where the exact solution exists. U exists in this neighborhood with U hat at the center, and rho is the radius, you see. Now the idea is very, very clear. So if we can evaluate alpha, if we can evaluate omega, then we can declare the solution existence. So we are talking about computer assist proof. So what kind of computation? So basically, we are considering some fixed point theorem, fixed point, right? We regard the solution as a fixed point. So Newton method is just to help us to calculate the fixed point. Of course, at the first stage, only approximate solution, but we can use this theorem to have some rigorous result about the range where solution exists. Unfortunately, so to have explicit value of alpha and omega is not it is really hard work. For omega, it's just about something about continuity. This is not so difficult, but for this alpha, so many problems to solve. So here I would like to introduce, you see, some early work. So on this problem, how to use Newton counter theorem to verify the solution existence. So in Japan, so in very early days, 1990s, so Nakao's group, he utilized the FEM, finite element method, to verify the solution to the Navier equation. So for 2D convex domain, so strictly speaking, it is the starship domain, not general 2D, or not general domain. It is the starship domain. Okay, from convex is okay, it's very nice. So non-code method use some information about LBB constant. So it is about the if condition for the solution existence. So you see, in 1999, a verification example is reported for stationary solution existence over square domain. So this is the first result. You see, to give some solution existence proof by using some computation result. But you see, in Nakao's approach, so he needs some explicit bound of the LBB constant. This constant, so unfortunately, you see, for 3D domain, even now, there's no explicit value of this constant. We have no information about the concrete value or some upper bound of that kind of constant. So basically, Nakao's method cannot be applied to 3D domain. And also, there are other approaches. For example, the people in Germany, the Bloom group, and also even Jean-Philippe method in Canada. So they are considering the solution existence. Basically, there's some reduced problem in 2D domain. So for 3D, it's really hard work. So okay, the LB constant something like this. So Ledytinskaya and Babchik are these constants. So given domain, okay, let's consider the domain D as 3D domain. So V space like this. This is the velocity space. And Q is the space function L2 with zero mean. Yeah. The constant is something like is defined in this way as an if zip condition. So for general FEM, so we cannot obtain the result that satisfies the divergence-free condition strictly. So basically, you see, if we obtain some U hat approximate solution, so it's not strictly divergence-free. In that case, this LB constant is required for the solution verification. We need some explicit bound for this beta. Yeah. For Starship 2D domains, there are some theoretical results for this constant. For general 2D domain or 3D domain, so there are no result. Recently, you see there's a group in Germany, Dietmar Galesto. So he had one result. He published one paper to compute the value directly, but you see just under some assumption. But this assumption is not clear. So generally, so as a result, you see, even now for 3D domain, so we have no information about the explicit bound of this beta. So yeah, then what help with how to give the proof for the solution existing in 3D domain? We have turned to some new method. Okay, so I would like to summarize, you see, the difficulty in solution verification for AS equation in 3D domain. So you see, the first one is about some projection error. So if we utilize, for example, FEM method, so we have to define projection from the original space, this is finite dimensional space, to some FEM space. FEM space, it is finite dimensional space. So then we need some equality like this. So U, we can regard this U as the exact solution or general function from the original space. Yeah. And PHU is something like FEM solution. So this is about error estimation. So given F, we have exact solution unknown. PHU is computable. How about error between each other? So there exists some constant in many papers, in most papers. So the people only have the information about the existence of some unknown constant. So it is bounded. It exists, but people have no information about the explicit value of or explicit bound for this CH. So this is very difficult to have some result, some value, and also, to give rigorous computation, to give computer-assisted proof for solution existence, we need to solve many unwanted problems. There are many constant, basically constant problem, just reduced to the unwanted problem. For example, for the Poincaré constant, if we want to evaluate the exact value or exact bound, sometimes exact value basically not possible, but we can have some upper bound. So then we have to solve some unwanted problem. So this is about the Stokes operator. So we have to obtain rigorous bound for some unwanted problem. And also the estimation of the norm, this operator. This is the fresh derivative at F. So this is also hard work. So many things are reduced to the unwanted problem. For this one, you see it corresponds to the spectrum of the non-self-joint Stokes operator. Yeah, it's much harder to handle. So here I would like to introduce what we have done in past 5 years, around 5 years. So first one is about the projection error estimation. So the basic feature about this method is that we use some divergence-free FEM. So it means, you see, we apply FEM, obtain some approximate solution, and this approximate solution is strictly point-wise divergence-free. And by using such kind of FEM solution, then we don't need the explicit bound, explicit value for the LABB constant. So here we have go to some details about FEM setting. Anyway, just a short introduction. So it is called Scott-Ordilis type FEM. So it's a piecewise polynomial, and with some test function. So the FEM space defined like this. So of course we cannot confirm details here, but we can confirm what kind of space it is. So for any function in this FEM space, so of course it is computable. This is in finite dimension space, and we have some test function Q. Yeah, Q is from this space. So this space is well defined in the meaning that this test function is dense enough to force divergence U being 0 point-wise everywhere. So the any trial function in this space, it is divergence free. Yeah, this is very nice. Of course, for computation, so it's a little the complexity, yes, it is a problem. But anyway, we can compute by using such kind of FEM. So we can have some divergence-free solution, but it is not exact solution. How to estimate the error? So here we turn to the very helpful method. It is named the hypercircle method. So, well, you see so many things about mathematical details. Let me introduce the basic idea. Maybe let's go to this page. Yeah. So to draw image, what kind of hypercircle? So hypercircle is, of course, it is a circle like this. So we have three terms, triple group. So U, P, V. So U, we can regard U as exact solution. The exact solution to what kind of equation? So for example, Stokes equation or Poisson equation. Yeah, if we forget our current topic, let's go back to our textbook about a very simple model problem about Poisson equation. Yeah, U is exact solution, and P is approximation to the gradient of U, and V is some approximation to U. We can regard it V as FEM solution. So basically, we don't know the exact solution. U is unknown. Yeah, this is solution to the Poisson equation or to the Stokes equation. So this is unknown. Yeah, this is from infinite dimension space. But P and V, we can use some trick to construct them explicitly. For example, V from FEM space. This is from another kind of FEM space. We usually call it mixed FEM method. Yeah. So both P and V, they are computable. And then what we can have from this circle? So the equality is something like this hold. So U unknown. It means we can regard this as error. So we want to have explicit information about this error, but this is unknown, right? The good thing is that we know we can compute this part, this edge length. So the right hand side term is computable. Then we can give upper bound for each error. So this is the power of this hypercircle method. We can use computable term to have rigorous computable bound for the error. Yeah, exact solution, approximate solution, error is computable. The upper bound is computable. So, well, this is too detailed thing because so many kind of FEM space. XH piecewise polynomial, PH is something like the approximation to the gradient, and which is FEM. It's called what is FEM. A good thing is that you see this term kappa H is defined on finite dimension space. So we can calculate this kappa, yes, by solving some matrix angularity problem. Everything is finite dimension space. So, and then we can have kappa H, and also we can have some constant quantity C0. C0 is just interpolation error estimation. It is easy to obtain some upper bound. By using this kappa H and C0H, we define this H. Then this works. So something like this. Given U, we define some projection, and U minus PH U is bounded by some term. So F is given, right? CH is computable. For kappa H and C0 is computable. So we can give some explicit value, some concrete value for this error. This is very important for computer assist proof. We want to verify some fixed point. We need to verify the contraction map. So we need to know. So for example, so alpha and omega, the production whether is less than half or not. So we need to know the value for all terms. So now for CH, it is well done. So the second problem is about eigenvalue estimation. So let's start with these examples for the Poincare constant. So this is very common in most textbooks. So given H10 function, so H2 norm is bounded by some constant produced by the gradient norm, the gradient energy norm. So if we want to evaluate the upper bound of C1, basically we have to solve some unvalued problem about the Laplace operator. So well, this is also well-known unvalued problem for Dirichlet boundary condition. Yeah. So if omega is spectral domain, scalar domain, then we can solve it theoretically. We have some closed form. But for general domain, we tend to computer to calculate it. So for the Poincare constant appear in the study of the Navier Stokes equation, we need some further condition like this, divergence free. Yeah. If we want to evaluate C2 for this inequality at norm and energy norm C2, then we have to solve the Stokes operator. So minus Laplace U plus the gradient of pressure, something like this. Divergence free there, divergence free condition there. Yeah. So basically, we can use, for example, FEM to help approximation for the eigenvalue. But we need some rigorous information. So it means so the bound for the eigenvalue, lower bound and upper bound. So here you see I would like to introduce just you see a very very powerful result that's obtained in past 10 years. You see. So this is one of my work on eigenvalue problem. So here is the general framework for bounding eigenvalues. So we can define eigenvalue problem in some space V, for example, H10, and we can use FEM space which is not necessary. Okay, not necessary subspace. So we can define projection, from the origin space to this FEM space. And we assume there exists some constant like this H. If we have explicit value of H, then we can have lower bound like this. So for each eigenvalue, we have lower bound. So basically, for upper bound, we can use min-max principle. It is very easy to obtain some upper bound. But for lower bound, it's very hard work. But now, so in the past 10 years, we have, in some sense, we have solved this problem very beautifully. Yeah. So with computable CH, the lambda KH is just the eigenvalue of some matrix. This is computable. And CH, I would like to show you some result about CH in next page. So basically, CH is computable, lambda HK is computable, then everything is clear. So for example, we can use the CRFEM, project Rabi FEM, to introduce some local divergence frame solution, and then we have explicit value for this stage. So yeah, this value is very special, very beautiful, because we are using some property like projection equal interpolation for CRFEM. So it means for Stokes operator, we can calculate eigenvalue. We can one by one. So for each eigenvalue, we have lower bound, explicit lower bound. Upper bound, we can also obtain. This is the trivial work. So now we can have you see, rigorous information for the eigenvalue problem. This is some result. So, okay, yeah. For example, for the Poincare constant, we can use some mesh like this to have sharp upper bound, and also we can have some lower bound. Yeah. So now I would like to show you some example. So the result for my paper now 3 years ago. Anyway. So we are considering the domain, three-dimensional space. Omega is, well, from this equation, it's difficult to imagine. Let me show you, okay, this graph. So this is the cube with the hole inside. By such kind of definition, configuration, this is a non-convex domain in three-dimensional space. So, because there's hole, and also around the corner there will come some singularity. Let's go back, something like this. And F given like this, epsilon, okay, not very small, but value like this. We want to verify the stationary solution for this setting, right? Yeah. And we use some special mesh, and we use the Scott Wojcicki FEM and also Navier Thomas FEM space, because by using this FEM space, we can have some hypercircle, we can have some rigorous error bound. And this is the result. You see, we can calculate approximate solution like this. So you can confirm the streamline. Yeah, it flows around this hole, and also from the center, it comes out from the back to the front, and yeah. So we can prove that, you see, with many quantity, computable quantity. For example, CP Poincare constant and the CH projection error estimation and some norm estimation, and also the where is the omega? Well, omega is not written there, but you see, we can calculate alpha omega by this term less than half. So each term is commutable. Then we can declare that the solution exists in this range with radius like this. So we have some approximate solution. We can define neighborhood, the neighborhood with explicit radius, and the exact solution must exist inside. We don't know where it really exists, but we know it must exist in this range. So this is the power of computer, the power of mathematics. So we can prove the existence of some fixed point. So this fixed point is just the solution to the Navier-Stokes equation. So the second part is about the ongoing work. So maybe I would like to be 5 minutes. Okay. So recently, there are some results, some reports that by some special setting, we can obtain two solutions for the same initial condition. So this is from the group from CBRAC, the group. So the paper appeared 2 years ago, but the preprint, I think, more than 5 years ago. So in their paper, so they reported the two solutions to the same initial condition. So if equation has two solutions, it means this equation is not so good. So this is some numerical evidence that tells us the Navier-Stokes equation maybe is not correct. Yeah, it's not well posed. Yeah, because with some initial condition, it can produce two solutions. So the basic framework to confirm this is multiple solution. It used, I think there are some words. So they are using the where it is? Wait a moment. Self-similar solution. Self-similar solution is something like this. It first defines some profile solution, and then by using some trick to define the solution, including the variable t. Maybe the detail not here. Well, okay. So basically, people have to first solve this profile equation. This is about this. In this equation, there's nothing about t. This is a stationary solution to some nonlinear system. This is not Navier-Stokes equation, but it includes the diffusion term and also some nonlinear term inside, and also a divergence-free condition. And also, by using the solution to this equation, it defines the operator. So this operator is a non-self-adjoint operator. By using the solution to this equation and also the eigenfunction to this equation with some proper value of sigma, it can define two solutions. Yeah. So then now you see now we are working on this problem to provide a rigorous result, to provide a computer state proof for this multiple solution, because this is only approximate computation. So many errors inside. So now it is not a mathematical proof. So we want to provide some rigorous proof. So you see, yeah, time is limited. For example, one of the problem to solve. So for example, for the divergence-free condition, so that solution is defined in a cylinder domain. So the solution is axis symmetric. So in this spatial domain, in this spatial coordinate, the divergence-free condition becomes something like this. So yeah, this is divergence-free condition. So unfortunately, you see for such candle equation, there are no FEM to provide divergence-free FEM solution. So we have to define some numerical scheme to provide divergence-free solution to this equation. Yeah. So we have some result. We introduced some idea. Where is it? Wait a moment. So yes, by introducing new variable, yes, this is around radius direction, and this is around the z direction. And we multiply the original function by r, and then we can transform the divergence-free condition to be something like this. So this can be handled easily by using current techniques. So something like this. Everything is ongoing. So for example, we have to develop some divergence-free FEM. Now this work it don't work with Professor Shang Yu Zhang, in Delaware University. Basically, now this is well done. And for the hypercircle in the cylinder domain, there are many work to do. And also, for example, currently we are working on we have some result about the solution exists on finite domain, but with multiple solution we have to consider something on unbounded domain. So, and also for the unbounded problems, so we need to use some homotopy techniques. To first focus on the finite domain and then extend to the global infinite domain. So and also we need to solve some non-self-joint unbounded problem. This is ongoing work. We hope to finish in the coming 2 or 3 years. Okay, yeah. Okay, Now I would like to stop here. This is last page.
Now question.
So if there are any result, if we solve the PDE by neural networks, for example, PINN.
Okay.
Yeah.
You see, I usually I have been asked by other people for almost the same question by using, for example, PI method. We can have some approximate solution, right? And we can use this one as a starting point for the Newton quadratic theorem. So it also works. So if the solution is smooth, it belongs to H1 zero space, then okay. And also we can map, you see, the solution to something like that, you see, to in the H1 zero. So basically the solution, the answer is yes, we can use that kind of solution. Yeah. Just theoretically it works. Yeah. I did not try that method for the moment. You see, something like this, to have some approximate solution, this is not hard work. We can use many numerical schemes. The most difficult thing is to give some rigorous estimation for the function approximation. And the hypercircle may be helpful. Yes, for example, PI method, we have some approximate solution. We can apply the hypercircle for further error estimation. So something like that.
Any other questions? If not, let's thank the speaker.
Yeah.